Everything's set up or it won't take off and run. So this is this one-line diagram project that we were going to do, and I want you to, if you have questions, today is the day to get them from me, because I think that I said, didn't I say that by next Thursday you got to hand this in? Is that right? Something like that. So if you are having any questions about it, maybe we can get those answered today. Um, I'm not an expert on this, and I've not worked through all the parts and pieces of this, so you're going to have to bear with me just a little bit. But we're going to go through it, and I do have an answer key, so we can kind of check that out a little bit as well. So anyway, so this is a one-line drawing, and there's a utility that comes in from the main, from outside, and you would show that as a transformer. Okay. And then you would bring that into your main panel and main distribution panel board, and you would call that MDP or whatever. So you would basically bring this into a panel board, and you would go to a circuit breaker of some kind. Okay, this would be in my main distribution panel board, or you can call it MDP, main distribution panel board. Okay. Now, from there, you got to size this at a certain value, and then you also have to size the transformer. For incoming power, indicate utility transformer and label it utility company transformer 300 kVA. And so you would do that. So you would label that up here. I'm not going to do that for you. You can do that yourself. This is 12.47 kV in primary, three-phase, 300 kVA. So the 300 kVA is your total power that you can get through this guy. Okay. Any questions about that? But that should all be listed right up here. All this part right here should be listed right there. For the MDP, indicate a 400 amp, three-phase, four-wire main distribution panel with 400 amp main circuit breaker and label MDP. So right here, you would say something like 400A, and then what does it say? Label MDP, main distribution. Okay, so that gets you started. So far, so good. Nobody's failed yet, right? Now it gets fun, right? Because now you're going to go down and you're going to start sizing the various things off of this. So here's your one line, and it comes down. And you can do this any way you want to, but basically like this would be fine. And then you're going to go down from that. Okay. And you've got four things you're going to put on there, right? You got four drops. All right. Something like that. So far, so good. What's the first one? 100 amp, three-phase wiring distribution panel board. Okay, so that's that. Okay, now indicate a branch circuit panel board fed from MDP. Indicate 100 amp. Okay, so now we're going to drop down at this point with a 100 amp breaker. And then we're going to size some wire, and then we're going to go down to a panel board. Okay, so this panel board is made lug only. It's a panel board down here someplace. So we're going to do this. MLO stands for main lug only. There's no main circuit breaker on this puppy. You use your circuit breaker up here to turn it off. Okay. And it's shown something like this. With a line down and then like this. And then label down here. And that label is this, all this information right here. Excuse me, all this information right here. So all this information, I'm not going to do it for you, but this is the information labeled that you would put right down here. Okay. And you've got to fill this wiring. What's the wire size for that? There are three of them. Three number something. And then one neutral. Some gauge wire. Okay. These are you're gonna have to do this. I mean, I'm not gonna look this up for you, but we're gonna have to look this up. Okay. You're gonna size a conduit. Such and such a size conduit. So many inches size conduit. Okay. Piece of cake. Good.
And then the other three branches are,
They're going to be listed right here. Okay, so one of them is a 45 step down transformer. So this one is a 70 amp. Well, it says size and indicate the circuit breaker in MDP feeding the transformer of this thing. Okay. So it's a 45 kVA down here. So this is a circuit breaker that feeds a transformer. It's 45 kVA. Okay. No, it's what's the size of these wires and what's the size of this what's the size of these wires and what's the size of this? Well, you got to size it, I think. Let me see. What 1.45 divided by 1.732 times 480 is equal to, okay. Comes up to about 54 amps. But you got to size this bigger than that, and you got to go up to the next biggest size, which I want to give you a clue here. It's a 70. This would be a 70. Okay. So this has to be, if you have a 45 kVA transformer, so your total current here, primary, is about 54 amps. Okay, 54 amps. This has to be sized a little bit bigger than that. I think about 1.25. I'm not sure of the number, but I think it's times 1.25. So you got to go to 1.25. That's 67. You got to go to the next biggest one, the next biggest one, which is 70. So that's what it's 54 times 1.25, and then you go to the next biggest one, which is a 70. Okay, everybody agree with that? So far, so good?
Where did you get 1.45 and 1.732?
Okay, so this is a three-phase. This is three-phase. 54, excuse me, 45 kVA is the watts. So what is the current? Well, watts or power is equal to what? V times I. So this is equal to 180 volts times 1.732 for three-phase. Okay, and this is 45,000. 45 times 10 to the third is equal to 480 times 1.732 times I. So what is I? You just drop off the 10 to the third, 0.47, and you get 54. Okay. Now, I wasn't sure about this, but I'm pretty sure that this guy's got to be rated at 1.25 of this. Okay. If you read your National Electrical Code, I think that's what this was sized at. Okay. So you get 1.25 times 54, you get 67. Well, you don't get a 67 amp breaker, so you got to go to a 70. So you size that accordingly. Now, once you size that, this wire between here and here has to be sized for 70, because that's what this will let through. So you have to size that wire for a 70. So you look at where's my break for what gauge wire, okay? And typically you do not use odd gauge wire, you use only even gauge wires. When you get to larger sizes, you only use even gauge wires. Now, some people don't do that, they'll use odd gauge wires, but most electricians do not carry odd gauge wires. They carry even, so you have to go to the next even gauge wire size to do that. Or you want to be a stickler, just put the odd gauge in, and if it's the one, it fits. But again, I don't care. I'm not going to build this. I'm just saying, and I'm not going to take off. I'm just going to see if you can go through the process and try to get it. Okay. So now you got down to that point, and then you go to it says it's a 112, it's a 12208. And they use a 225 amp main circuit breaker, but they only put the size in there for 150. So they use a main circuit. They undersize the main circuit breaker. Okay. So here you use a panel board that is appropriate. Okay. But you have to use a circuit breaker that is appropriate as well. So basically, this point in time, 208 is, so now you're down to calculating the size of the circuit breaker for this panel. Okay, so now I come down to this panel. And it says to use a 225, which makes sense because the sizes are 100, and then I don't know if is there a 200 or is it 225 next size up? I don't know, but he says use a 225, so you're going to use a 225 here. But you're going to have to put a circuit breaker in here that's a main circuit breaker that's under that because you can't load this up to 225 amps. You can only load it up to what this can do. So how many amps can you carry on this wire? Well, it's 208 is your primary voltage. So basically it is what? It's 45 kVA is equal to 0.208, or excuse me, 0.208 times 1.732 times I. So what is that I? 45 divided by parenthesis 2.208 times 1.732 parenthesis equals 124, which is right at 125. So you can carry, you got to protect this with a 125 amp breaker. So this is why there's a 125 amp breaker in this thing. Okay. It's a little confusing, but it's all very doable when you're laying this out. Okay, now, what else is there here? Any other biggies here? What do we got to do? Well, this is what I'm accustomed to with these is a circuit breaker and a motor. Okay, so you go down to a disconnect to a motor. Okay, many motors in most applications where you're doing an industrial application. So you'll have one after the other, after the other, after the other of these. Okay, you might have 50 to 100 motors on a one line for a process. There's a bunch. So you have all these motors on there. Okay. Now, what's the size of the motor? 15 horsepower. Okay, so you're running this at what? 40 volts. So this is all 40 volts up here, right? 40 volts three phase. So you're running at 40 volts. Now you got to go back up here and calculate the what? Circuit breaker. Now is this circuit breaker just to, oh, it's a variable frequency. It's a VF. It's a variable frequency controller. Okay, all right. Now it's going to have a labeling on it, and it's going to say all the things that you need because it's a variable frequency controller that it basically is going to tell you what it needs. And this is where you just basically read through the directions of what it is, and you say, okay, um, what is it going to, what is it we're going to, what is it that we're going to need here? Okay, so here is a 15 horsepower motor, air handling unit. What would it take for that? Okay, so 15 is about 15, what? It's 480 times, okay, so it's about 15 amps. All right, so you can have about 15 amps going through here. The amps is usually about the same size as about that, all right? At 40 volts. So that's about right. Now he sized it with a 40 amp main. And you can use that 40 amp in the sizing of the wires accordingly. Okay. Now, this other one over here is nothing more than a spare breaker, so 225 amp breaker. And you can size the rest of it yourself and come up with the answers that you come up with. I didn't want you to get off in left field. I wanted you to kind of have a starting point. That's why I did this. But I'm not going to give you all the parts and pieces. You just figure it out the rest of the way by yourself. Okay? And again, there's variability in the answer. I'm not going to hold you exactly to the answers that I have right here. I'm not going to do that. But you should go through the process and but my experience with motor with one lines is you have 20 to 50 of these guys. Lots and lots and lots and lots and lots and lots of motors. And this is not the only thing what you see, because we're going to get into this next half of the semester. You're going to find that people stand around a water cooler and argue about how to control these things. You're going to find all different ways. Well, if you do this, then this, and this. I got, that was not my area of expertise, and I could see disadvantages and advantages of all the different ways of doing this. Some people like this way, and some people like that way. We're going to talk a little bit about some of the variability that you can have in a motor starter circuit. But that's all I'm going to do about that right now. Anybody have any questions? Piece of cake, pretty straightforward. I want you to be able to, I do not want you walking into a plant and saying, what is a one line? That would be the worst thing in the world. And the second thing would be to not know how to, what happened? Okay. Would be to not know, I don't know, just, believe me, it's good if you have some ideas about how to do this sort of thing. Okay, next. I want to talk a little bit more about harmonics, and this is okay. So at the end of this book right here, I added a little thing in the last night about now we don't really care. Okay. This is what I asked about, and I talked to you about this the other day. I asked Mr. ChatGPT, are harmonics less today than in the past due to improved inverter design? And they said yes, in general they are, because in the olden times they had what they called 6-step inverters, and the inverters of the modern inverter does not work that way. The old inverter looked like a stair step, and then we got smarter and we started building inverters that were much more that were much less heat intense. So the older inverters, the 1960s and 1970s inverters, look like this. Trying to build a sine wave out of square waves, okay? That did not work very well. And that caused all kinds of heat-related problems with motors. And that's why they didn't last very long. Okay, so that was the old style. And then they started doing this. They started actually taking and turning on with the same height. These will get closer together. And then you get a big one, and then you get some little ones closer together. And then you get further apart, and then you'd start down this way. Okay, now the reason for being able to do this is because you can vary the width of this, and you can vary the width of this. The way to vary the speed of an AC motor is to vary its frequency. So this frequency here, you're trying to emulate this. So if you wanted to go faster, you would make it a higher frequency. Okay? If you wanted to go slower, you would make it go slower, like that. Okay? So slow, intermediate, little fat. This is, I guess, a little faster than this one. Anyway, they're you vary the frequency and you vary the speed. That's exactly how it was done. And this did it very hacked up. This did it much more elegantly. And the whole idea of this was to be able to switch these as fast as possible and also watch for the feedback of the current. So basically, you did this to the voltage so that the current actually did this. The current actually emulated a sine wave. So voltage is these peaks, current is this guy right here. Now, what is wrong with this is that these guys here spit out harmonics. So you have harmonics with these. Now, why do you have harmonics? Well, because anything other than a pure sine wave is going to give you harmonics, and these are not pure sine waves. Anything other than a pure sine wave is going to give you harmonics. So the only thing that does not give you harmonic is this guy right here. Anything else will give you some harmonics. And if you even have a distortion in your AC waveform, if it does this type of thing, you have harmonics. Okay? Now, I'm not trying to prove to you today that you can calculate these harmonics, but what you want to do is you want to get rid of them. Okay? So this is called Fourier analysis. And Mr. Fourier was a mathematician, French mathematician, and he did this. What the heck is going on? I don't know. Called Fourier analysis, okay? And I'm not expecting you to do this calculation here, but I want to show you what you can say. You can actually see that anything other than a square wave is the same. If I have a square wave, it's the same as saying a sine wave with a bunch of higher frequencies. So you can start by saying, okay, now I want to make a square wave out of a bunch of sine waves. And you may not believe this, but it actually is true. So what is this waveform? It's this one plus this one, which if you start looking at these, adding them up, this looks a little bit more like a square wave, doesn't it? If you add another one, you could get a little bit more. And when you add up the first 20, you get looking like that. Now that's pretty close to a square wave. It's not exactly a square wave, but it's pretty close. Okay? And if you go to 199 harmonics above it, it looks very, very close to a square wave. Very close to a square wave. And if you go infinitely far, it will look like exactly a square wave. Now, how do you get these constants? And what are these constants? Okay. How do you find these numbers? Three x over 3, 5x over 5, 39x over 39. How do you get those? Well, there is a formula that you can actually try that will actually bring that out, okay? And here it is. I know you're not impressed, and I'm not impressed either, but that's how it is. It's the integral of the function cosine of nx times pi over L. And out plops these numbers. Okay? And some of them are going to be 0. And some of them you're going to integrate and you're going to get the numbers. So basically, it is a process of finding those numbers. Now, you're never going to ever just say, okay, this waveform is a sine wave, but it is. It's a bunch of them. And as you go up in frequency, their higher frequency ones there are harmonics in them, and you can assume that there are because there are. Okay. Now, this goes through the process and it finds these numbers for you. And again, I'm not going to try to give you all the details about how this is done, but this is exactly what is happening. And so at the end of the day, you have a function with these numbers, whatever they are. Okay? How do you get that number? It is through the integration process. You can actually calculate these. And that's basically what they are for that square wave. So if you want to find what those numbers are for that square wave, it's 4h over pi, where h is the height of the square wave. So as you go up, it's 4h over pi for the first one. It's 4h over 3 pi. Then you go to the third one, and it's third one is it's 4h over 3 pi for the third one. Then it's 4h over 5 pi for the fifth one. And those are the numbers that you're actually going to use. So here is the numbers for the actual numbers for a square wave and all the harmonics. So if you wanted to know what a square wave that's equal on the top and on the bottom can be represented by a sequence of numbers with signs, here they are. So here's my square wave. And here it is. Of height h. And there are my signs. There they are. And there's the height of each of the ones as they go up in order. So notice that as they go higher, they get less, but they don't go away until they get really, 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 really big. But that's it. All is to say that there are harmonics in a lot of your waveforms, and you got to get rid of them. Okay? You cannot let them do damage to other pieces of machinery. You have to get rid of them. And that's why when you buy an inverter, that basically has the filtering in it that does not allow the inverter to allow these harmonics back on to the AC waveform that's feeding your inverter. You do not want that. You do not want this junk to escape back upstream into the rest of your circuitry. And there's why. These are the things that you don't want. You don't want those. Okay, that's about it. We're going to start on next week on Wednesday of next week. We don't have class on Monday. We're going to start next week on motors and motor control circuits. And anyway, that's what we're going to start there. The circuitry for the inverter we don't get as involved with, but we do have some inverters, and we are going to actually watch these. You can't see the harmonics, but we're actually going to watch the waveforms of the output of the inverter to the motor. Harmonics also play a part in a number of areas in troubleshooting. And they call it fast Fourier transforms, FFTs, fast Fourier transforms. So you can put an accelerometer on a motor and it will tell you when the motor is going to fail. And you can also do a fast Fourier transform of the AC waveform of a generator, and it can tell you when it's going to fail. And it's fast Fourier transforms are very useful in a number of applications because as these harmonics start to grow, they will tip you off that it's premature, but it's gonna happen. There's a bearing that's gonna go bad, something's gonna go bad, probably mostly mechanical, but they are gonna start deteriorating very quickly after you see these FFTs starting to go. And they are done. People do study FFTs. They do take them and look at them, especially in applications where the machinery has to run. They do this. They actually measure the vibrations and they do a fast Fourier transform of it. And that's if you've never heard of FFTs before, that's exactly what they're useful for. And it's because of this thing right here. This is a Fourier transform. Okay? That's a Fourier transform of a square wave. Any questions about that? So you will hear of FFTs, fast Fourier transforms. You will probably never see this again, other than the fact that it can be done. But you will get people that will give you information about, well, if you have an FFT, and then they can tell you from the analysis of your waveforms when things are going to start failing. And that's why they're used. Okay? Anybody have any questions? Any comments? I don't know how soft starts work. Why do soft start motors not cost as much as inverter? If you're going to buy a motor, do you have to always ask the question, do I want a soft start versus a motor? I'm going to talk a little bit about the soft starts eventually, but soft starters use SCRs, silicon controlled rectifiers, instead of IGBTs. IGBTs cost more money, but they're higher switching. These guys, what they actually do is, here's your sine wave, and they only allow through a certain amount. So they start here, and they turn off when you go through zero. So in other words, they turn off when you go here. So you allow that much in. So you turn it on right here, and you only allow that much in. Then you turn it on a little bit later, and you allow this much in. You keep moving it across until you finally let the whole thing in. But basically, all it can do is, at some point in your sine wave, it turns on. And then when it goes through zero, it turns off. It comes back here, turns on, and then it turns off when it goes through here. That's all it is. SCRs. They're big power. You can use them for high power, but all they do is allow you to ramp up your speed. They do not control your speed. So once you get up to full speed, they're useless. Okay? They don't control your speed. And I had a guy that I worked with that okay, so are there examples of things where you adjust the speed at a later date? And there is. With the ovens at Owens Corning, if you heat an oven up to 400 degrees, it's less horsepower once you get the fan up, once you get the heat up to 400 degrees than it is when you're at ambient. So in order to heat the oven up to 400 degrees Fahrenheit, this is where after the fiberglass has been spun and it's still wet, it goes through an oven to dry it out before, you get it at the lumber yard, it's dry, right? Well, when they make it, it's wet. So they have to take it and put it through an oven to dry it out. So these ovens run at 400 degrees, okay? But in order to get the oven up to 400 degrees, they have to run it at 60 horsepower. But then when you're running at 400 degrees, the because there's fewer atoms in the air at 400 degrees than there are at 75 degrees, it takes 40 horsepower to circulate the air in an oven at 400 degrees. All right? So one of the guys got this bright idea, well, I'll just use a soft start instead of an inverter. So you save money if you run it at if you run it at 40 horsepower. Okay. So what they did was they said, okay, originally they ran it with DC motors, and they ran them 40 horsepower DC motors, but they would run them slow. They would just run them at a slower speed. And then when they got up to 400 degrees, they had increased the speed up to the regular speed of the motor, and then it worked. But DC motors have an inherent problem in that they got brushes and they've got a maintenance issue. So you don't want to do that, and they cost a lot of money. So what they wanted to do was they wanted to go to inverters, because inverters, you can run them at a slower speed, and then when you get to 400 degrees, you can raise them up to the regular circulating speed, and you're running on 440 horsepower, and you're good to go. So you run 40 horsepower, that's all you need. So what he did was he bought a 40 horsepower soft start, hoping that it would, by the time you got up to full speed, you'd be at 400 degrees. Didn't happen. Wasn't even close. And you couldn't control it. So he had all these soft starts that he bought for this one oven application. He had to take them all back and then put in inverters. But anyway, that's an application that you do not want to, you don't want to misuse soft starts. You don't want to use them as kind of as a cheap version of inverter, because they don't work. You can soft start a motor, but you can't control the speed of it. Once it takes off, it's going to go. It's just going to keep going faster as it goes. Anyhow, some of the experiences at Owens Corning that I just heard about, I didn't ever do that. I would never do anything like that. I'm not a motors guy either. I didn't do a lot with, there was a lot of that kind of stuff that other guys did. I didn't do it. I was a programmer. All I liked doing is what I did and whatever. But I heard a lot of stories. I did some motors, but I didn't do a lot of the big stuff. And again, none of us did really big stuff, because all that was done by the power guys. Anything over 300 or 400 horsepower went to the mid voltage range, the 4160 horsepower, 4160 volt motors, and those all were done by the power guys. I never started up one of those motors. I was scared to death of that. Anyway, by the no lab this week, and you should hand in your quiz if you got a quiz this week. There'll be you can hand in your quiz if there's a quiz, and I'll check those over. And then there's one other thing I'm going to assign you, and it's basically here. And I forgot about this, but again, you have until after the break, the Wednesday after the break. But I added this is a book on harmonics, and I'm not carried away with harmonics, but this is an extra, and it's in your website. It's on harmonics, and it talks about harmonics and all that kind of stuff. And I added a homework assignment to you that's on your website, and it is there's a 10 question thing on that book on there. So you've got this one, you got this one, homework 3, 4, 5, and 6, and then number 7. Eaton's white paper, blah blah blah. There are 20 questions. Oh, that's so much fun. And in order to get your 20 points, there's 20 questions on that one. But it's just to read through, have the 20 questions out when you're reading through it, and not a biggie. But again, just a
And that's due next week,
huh?
homework 7 too.
This is homework 7. That'll be due also after the break, the week after the break. Yep. Wednesday, I'll be here basically collecting stuff. I don't know if I've got any lecture material or not. I'm pretty well done. We will meet. I will be here. But again, I'm not saying how long I'll be here or how much we'll do, but I'll be here, okay? So answer questions. There probably won't be much lecture, but I guess but there will be, you don't have a test. Your test is your test is those two things, the one line and then the other thing you're supposed to answer on. You remember?
The Eaton text.
Huh?
The Eaton text.
Yes. What?
The Eaton text.
Yes, yes, the Eaton,
How much
yes.
do you want for that? Is it, I mean, just like a page of,
Yeah, a page would be fine. I want you to review that text and at least you know a little bit. You don't have to, you don't have to be an expert on it, but I tell you what, walk out of here, you ought to know where to look. And that's about all I can say. And we're gonna talk about motors after a while, after this, and well, motors I got a little bit better of an idea about how to do. Some of this stuff I was a little scared to do sometimes, but I did it and it worked, and I never had anything that didn't work. Well, I had a few things that I had to change around a few times, but basically it worked. But I stayed away from the high power stuff. I, I want to ask you one other question before you leave. If you walk up to an electric fence, or not an electric fence, but a fence around a distribution center, or where there's big heavy duty transformers out in a substation or something like that, how close do you want to get? How close is close? How close is close enough?
Close to pee on it,
Huh?
close enough to pee on it.
No, you can't. It'll in a dewy kind of heavy, misty kind of. It'll jump about a foot per thousand per kV per thousand volts. So if it's a 10,000 volt system in there, you want to stay about 10 feet away. Okay? You don't want to get close. It'll jump. Again, I never did, but I had an electrician. His name was John Cuppy, and oh my, this guy, he drilled me like he would embarrass me he loved embarrassing me. But on the other hand, I took it because I was learning like heck from the guy. He had fallen off of a ladder, but he was smart. He had done a lot of kind of stuff with himself as an entrepreneur, but he basically was an electrician. He's crippled, fallen off the ladder, but he knew the electric code book back and forth, backwards and forwards. And anyway, I learned more from that guy through embarrassment, but he'd say something, and I'd crawl back to my office and start reading about it, and yep, there it is. So anyway, I honor people that are mentored me, and John was one of them. He didn't realize he was. He's trying to embarrass me, but I took it, kept on going, but anyway. I did appreciate the people that were good mentors, and he did seem to care, and he did throw a lot of stuff my way, and I tried to take it, and usually, did I shut that off already? No, I didn't.